Alan Guth. The lecture hall is packed with grad students. He draws a curve on the board and says the early universe must have exploded in size. His idea was simple. A tiny fraction of a second after the Big Bang, the universe blew up in a burst of expansion called inflation. That burst explains why the sky looks the same in every direction. It also opens a door most people miss. If inflation happened once, it could happen elsewhere. In some versions, inflation never ends. Tiny regions stop inflating and form pocket universes. Each pocket gets its own physics. That is where the multiverse idea sneaks in. Guth did not claim absolute proof. He made a prediction that matched signals in the cosmic microwave background. Satellites like the Planck mission found patterns that fit his model. That turned inflation into serious science instead of just speculation. But there is a problem. If inflation never ends, you get an infinite set of pockets. You cannot easily assign probabilities. Physicists call that the measure problem. They argue about what counts as evidence when everything repeats somewhere. For some researchers, that gap looks like missing proof. For others, it is a warning. If universes are being born like bubbles in boiling water, we might never see another one. Or we might be living in a rare patch that tells a strange story about chance. His papers sparked a field of debate. Some scientists search for subtle patterns in the cosmic microwave background that might carry echoes of other bubbles. Others say that such signals are invisible by definition. The disagreement makes the hunt more urgent and more eerie. Scientists turned to the sky for proof. They scanned the cosmic microwave background, the faint afterglow of the earliest light. The idea was simple in principle. If another bubble universe had brushed ours, it might leave a scar, a cold spot, or a ring in that ancient light. Teams hunted for patterns that do not fit simple randomness. Some claimed hints, a cold patch, a strange alignment, a set of temperature variations that seem unlikely by chance. Others pushed back. They showed how noise and instrumental quirks can mimic a scar. The debate is honest and brutal. It is also practical. Telescopes record photons, and math looks for unlikely arrangements. If a convincing pattern stood up, it would be the closest thing to proof we could get from our corner of reality. But even a convincing pattern raises new puzzles. If bubbles form forever, you end up with infinity. Infinity breaks ordinary probability. That is the measure problem again. When every outcome repeats, you cannot say how likely any one event is. That makes evidence slippery. You might detect an echo and still wonder if it is unique or inevitable. Some researchers propose clever statistical rules to trim the infinity down to something testable. Others argue those rules are arbitrary. The fight is not only technical, it is philosophical. Do we accept a model that makes sense of data even if it multiplies worlds beyond counting? Or do we demand direct contact, something impossible for many bubble scenarios? The search continues. Data improves. The questions get sharper. And the possibility that our universe is one of countless others remains both tantalizing and stubbornly beyond final proof. André Linde. He stood in front of a chalkboard and pushed inflation beyond a single burst. His math said inflation could keep going in some places while stopping in others. Picture a boiling pot where bubbles form, but the pot never cools. Each bubble becomes its own universe with its own rules. The mechanism begins with tiny quantum fluctuations. In some patches, the field that drives expansion falls and reheats into a hot universe. In others, it stays high and keeps inflating. Those high patches spawn more volume and more chances for new bubbles. In one paper, he showed how certain rare objects could act like seeds for whole inflating regions. Those seeds expand and carve out new cosmic patches. The result is not just many worlds, it is a landscape of bubbles, each with different properties. That idea lets physicists explain why our universe seems tuned for life. If there are countless pockets, some will have the right recipe for complexity. That is useful, but it also feels unsatisfying. It hands us an answer by multiplying realities rather than explaining a unique cause. Linda and his collaborators even tried to estimate how many distinct universes can exist under reasonable assumptions. The number they reached is so vast that ordinary words fail. The scale changes how we think about probability and explanation. For some researchers, that is progress. For others, it is a retreat to anthropic reasoning. The debate is alive and fierce, and it forces a simple question that refuses to go away. If bubbles are forever popping into existence, which one is our universe, and why does that choice feel meaningful? They tried to tame the infinity with rules. Lind and his collaborators proposed ways to count pockets and to judge how typical our patch is. One approach weights regions by how much volume they produce. Another trims the counting by focusing on events that observers like us could see. The problem is, these choices change the answer. Different rules lead to very different probabilities. That unsettles people who want a single objective prediction. Lindy accepted the strangeness and pressed on. He and others wrote papers that estimated how many distinct universes could exist under reasonable assumptions. The numbers they quoted are effectively beyond imagination. That drove some physicists to search for evidence instead of relying only on counting tricks. Observers turned to the sky for signs that a neighboring bubble had touched ours. They looked for circular imprints in the ancient afterglow, patterns in temperature maps, odd alignments that refuse simple explanation. A few signals looked intriguing. Teams published hints and then retracted claims after better data or improved analysis showed the patterns were likely noise. The debate sharpened tools and made the search more honest. Lind himself remained pragmatic. He acknowledged that for many bubble scenarios, direct contact is unlikely. Yet he also argued that even statistical hints matter. If a pattern survives scrutiny, we would have changed the status of the multiverse from speculative to scientific in a powerful way. That possibility is both thrilling and terrifying. It means that what we call the universe may be one small face in a vast and ongoing cosmic reproduction. The idea that our home is one bubble among uncountable others refuses to settle into comfort or denial. Hugh Everett. In 1957, a young graduate student submitted a thesis that would challenge the foundations of physics itself. His advisor was John Wheeler, one of the most respected physicists of the era. The student proposed something radical. What if quantum mechanics means exactly what it says? What if when an electron can go left or right, it actually goes both ways? Everett said the mathematics of quantum theory should be taken at face value. No collapse, no observer effect, no mystical measurement process. Just pure math describing reality. His idea was simple but shocking. Every time a quantum choice occurs, the universe splits, one branch where the electron went left, another where it went right, both equally real. The thesis met fierce resistance. Niels Bohr, the father of quantum theory, rejected it completely. Other physicists called it absurd. Wheeler himself grew uncomfortable with the implications. But Everett pressed on. He showed how his interpretation solved the measurement problem that had plagued quantum theory for decades. No special role for observers, no arbitrary collapse. Just branching realities. The mathematics worked perfectly. Every quantum interaction created new branches of possibility. A cosmic tree growing forever, with each branch representing a complete world where different outcomes played out. Critics attacked the idea as untestable. How could you prove other branches exist if they cannot interact with ours? Everett replied that the theory made precise predictions about what we should observe in this branch. His advisor Wheeler grew increasingly worried about the reception. The physics community was hostile. Everett faced a choice between defending his theory and pursuing an academic career. He chose the practical path. After graduation, he left physics for military research. His revolutionary idea gathered dust for over a decade, ignored by most scientists. But the mathematics remained sound, and eventually other physicists would rediscover what the young graduate student had glimpsed. That reality might be far stranger and far larger than anyone had imagined. Years later, when his theory finally gained attention, Everett was working on nuclear strategy for the Pentagon. He had moved from mapping alternate realities to calculating mutual assured destruction. The irony was bitter. Max Tegmark. You find his paper on a cluttered desk, and the headline feels more like a dare than a theory. His central claim is simple and radical. The physical world is not described by mathematics. The physical world is mathematics. Every consistent mathematical structure exists as its own reality. In plain terms, if you can write the rules down, then those rules count as a universe somewhere. He organized multiverse ideas into levels and pushed the idea to its logical end. This is not a tiny tweak on cosmology. It is a change in ontology. The payoff is neat. It explains why math maps the world so well. If reality is mathematics, then discovery is the same as exploration of structures. The problem is evidence. Critics call the idea metaphysical and unfalsifiable. They ask how we could ever test for universes that are pure mathematical forms with no shared space or causal contact. Supporters respond that the hypothesis makes predictions about the character of laws we should see, and about what kinds of observers can exist. The discussion forces a hard question. Do we accept a theory that explains the uncanny fit of math at the cost of populating existence with every consistent structure? Or do we demand that science remain tied only to what can be observed and measured directly? That tension makes the idea deliciously uncomfortable. If the hypothesis holds, then mathematical possibility equals physical reality, and our sense of uniqueness collapses into a vast catalog of logical worlds. Supporters of the mathematical universe point to a strange fact. Math describes the world with uncanny precision. Tegmark turns that uncanny fit into a bold claim. If reality is mathematics, then the map is the land. For supporters, that explains why equations work so well. It also suggests testable expectations. If math structures host observers, then the laws we measure should belong to structures that allow complexity. That idea narrows the kinds of equations we should expect to find. Critics reply with a simple complaint. How do you test for a structure you cannot interact with? The answer splits the field. Some argue for indirect tests. They say the hypothesis constrains what our laws can look like, and that those constraints are falsifiable in principle. Others call that move an exercise in semantics. The more serious worry is ontological. Accepting every consistent structure as real multiplies existence without limit. That has odd consequences for meaning and responsibility. If every logically possible version of you exists somewhere in the catalog, then choices lose the sharp edges we feel they have. Tegmark acknowledges these hard consequences. He casts the hypothesis as a scientific stance, not a metaphysical comfort. He invites critics to point out predictions that fail. The debate has sharpened where science meets philosophy. It asks which we value more, explanatory reach or empirical contact. The idea is thrilling because it promises order beneath the chaos. It is unnerving because it replaces uniqueness with a vast library of possible lives. Somewhere in that library might be a version of you who took a different path. Brian Greene. He wrote a book that reads like a tour through alternate realities. He gives names to different multiverse ideas so readers can see how they differ. One model says the universe is quilted. Distant patches of space beyond our observable horizon repeat patterns much like patches on a quilt. Another model is inflationary bubbles, similar to ideas you have already heard. Separate pockets form in an expanding background. Then there is the landscape idea, where different regions pick different fundamental constants. Each label helps you picture a different kind of otherness. Green explains how these models come from different parts of physics. Some come from cosmology, some trace back to interpretations of quantum mechanics. The value of his approach is clarity. It forces the question of what counts as evidence across very different pictures. Critics point out a shared weakness. Many of these models push relevant signals beyond anything we can ever measure. Others offer indirect handles. They propose patterns or statistical expectations that might survive in our data. Green is careful. He treats each model with optimism and skepticism. He shows how one model might suggest a faint imprint on ancient light, while another leaves no trace at all. The result is a landscape of theories that are easy to describe and hard to confirm. That tension is the engine of the field. It also makes the hunt more human. Physicists argue about labels, predictions, and methods. The debate asks an urgent question. If the multiverse exists in any of these forms, how would we ever know we are not simply a patch on a cosmic quilt? Sean Carroll. You sit in a dim seminar room, and he speaks plainly about quantum choices. The many worlds interpretation says the wave function never collapses. Instead, every quantum outcome branches into a new history. That means every time a particle makes a random choice, the universe splits into parallel tracks where each possibility is real. In Carroll's telling, this is not mysticism. It is a straightforward reading of the math once you accept the universal wave function. The key physical idea is decoherence. Tiny interactions with the environment rapidly make branches non-interacting. They stop interfering with each other and behave like separate classical worlds. That is why you do not notice sudden splits in your daily life. Mainstream physicists divide on this. Some praise many worlds for removing collapse and for giving a clean, deterministic account of quantum mechanics. Others call it ontologically extravagant. They ask where the evidence is for all those branches. Carroll argues the interpretation makes sense of experiments and that it is conservative about the formalism. Critics reply that conservation of form is not the same as empirical evidence. Practically speaking, experiments probe quantum interference and decoherence. They show the mechanism that would produce branches. They do not show other branches directly. The dispute becomes philosophical and scientific at once. If every quantum event spawns a real branching, then the number of realities grows unimaginably fast. That idea touches identity. Somewhere out there might be an identical you who watched a different video or made a different choice. The thought thrills and chills at the same time. Experiments show decoherence in action. Researchers interfere tiny particles, and then watch the interference vanish as the system meets its environment. In labs using superconducting qubits and trapped ions, physicists control decoherence and study how branches would form. Those results match the math that Carroll highlights. They show how quantum possibilities become effectively separate histories. Yet the most serious challenge is probability. Many worlds gives a clear account of how branches appear. It does not immediately tell you why one branch has the weight we measure as a probability. Philosophers and physicists debated this for decades. Some propose decision theory arguments that try to recover the usual probabilities from rational choices across branches. Others seek derivations that tie the numbers to branch structure. Critics say those moves smuggle in probability by another name. Carroll answers with modesty. He says the interpretation fits experiments, and that work remains on the probability puzzle. The practical upshot is odd. Experiments confirm the mechanism that would make branches real. They do not scan other branches or send messages across them. So, in the lab, we see the how without seeing the elsewhere. The result is a picture that is scientifically respectable and philosophically unsettling. If every quantum event spawns a vast tree of realities, then consequences multiply with stunning speed. The multiplication changes how we think about chance, responsibility, and identity. The final question lingers in the air. Leonard Susskind. You sit in an auditorium as a speaker lays out a dizzying possibility. The basic idea is this. String theory admits an enormous number of ways to shape extra dimensions. Each shaping gives different values for masses, forces, and constants. The set of all these possibilities is the landscape. The count people often quote is so large it is written as 10 to the 500. That number is meant to shock you. It shows how many distinct low-energy worlds string theory can produce. The immediate payoff is tempting. If there are so many options, then the fact that our constants look just right for life needs less mystery. We live in a patch that allows observers. That is the anthropic move. Critics dislike that answer. They say it trades deep explanation for a selection effect. It can feel like giving up on prediction. Susskind pushed the idea hard. He argued that anthropic reasoning is a legitimate scientific tool when theory yields many outcomes. He also stressed statistical approaches that try to predict typical values among habitats that support observers. The practical testability remains slim. Some researchers hunt for correlations among constants, or for rare signatures left by transitions between vacua. Others study dynamics that might favor some compactifications over others. The debate matters because it changes how science explains fine-tuning. If fundamental constants vary across a vast ensemble, then our laws may be local facts, not cosmic necessities. That possibility is liberating and unsettling. It suggests that what we call the laws of physics are less like fixed rules and more like a choice from a cosmic menu. He called it tunneling from nothing, and he treated the phrase as a precise calculation. The unnamed physicist wrote down quantum rules and showed how a tiny fluctuation can nucleate a bubble. That bubble can inflate and cool into a universe with stars and chemistry. The math is tidy. The picture is haunting. Teams looked for traces that such events would leave. They searched gravitational wave backgrounds for unusual spectra. They scanned the oldest light for odd imprints that a violent birth might imprint. So far, the sky has kept its secrets. Candidates appear and then fade under closer analysis. Instrumental quirks and statistical flukes explain many early hints. Still, the search forced progress. New data sets and sharper methods reduced false leads and improved what counts as a signal. The deeper puzzles remain conceptual. How do you define nothing in equations that always contain fields and energy? What sets the boundary conditions that allow a fluctuation to grow rather than blink and die? Concrete models were proposed to answer those questions and to open the topic to debate rather than to mysticism. The papers invited rebuttal and refinement. The result is a productive argument where math meets metaphysics. That argument matters because it shapes how scientists will look for evidence elsewhere in the series. If universes can nucleate from quantum foam, then origins become natural events in a larger process. If that is true, the human story moves from singular miracle to one item in a continuing cosmic production line. The thought is simple and disorienting. Bryce DeWitt. In 1970, a physics journal published an article that would change how people thought about reality. The author was not the original inventor of the idea, but he became its most passionate advocate. DeWitt had read the work of Hugh Everett, the graduate student whose thesis had been ignored for over a decade. Where others saw mathematical abstraction, DeWitt saw cosmic truth. He wrote with conviction about branching universes and parallel realities. He coined the term that would stick: many worlds. Every quantum transition, he declared, splits our local world into countless copies. His article in Physics Today reached thousands of scientists who had never heard of Everett's interpretation. DeWitt painted a picture both thrilling and terrifying. Every quantum event, from atomic decay to stellar fusion, creates new branches of reality. The response was immediate and polarized. Some physicists embraced the mathematical elegance. Others recoiled from the ontological implications. DeWitt pressed forward, organizing conferences and editing books. He collaborated with graduate student Neil Graham to compile the definitive anthology on many worlds interpretation. The collection featured Everett's original long thesis, published for the first time, alongside supporting papers from other physicists. DeWitt's advocacy was crucial. Without his promotional efforts, Everett's revolutionary idea might have remained forever buried in academic obscurity. But DeWitt saw something profound in the mathematics. He understood that quantum mechanics, taken seriously, implied a reality far stranger than anyone had imagined. A multiverse, where every possibility plays out, where every choice creates new worlds, where consciousness splits along with atoms. The physics community remained divided. Some praised the interpretation for solving quantum measurement problems. Others criticized it as unfalsifiable metaphysics. DeWitt engaged all critics, defending the theory with mathematical rigor and philosophical boldness. His work helped establish many worlds as a legitimate interpretation, not merely a curiosity. Modern quantum theorists still debate its implications, but few dismiss it entirely. DeWitt had rescued a revolutionary idea from oblivion and given it the attention it deserved. Paul Steinhardt. He stood at the chalkboard and sketched a universe that refuses to stay dead. His cyclic model replaces a single beginning with repeating cycles. Each cycle ends with a slow contraction that smooths the cosmos and then bounces into a new expansion. The technical move, called the ekpyrotic phase, squeezes irregularities until space is uniform again before a bounce. In some versions, collisions between higher dimensional sheets drive the bounce. The claim is practical. It offers an alternative to a lone, singular birth, and it changes what we should expect to see in the sky. One clear prediction is about primordial gravitational waves. Cyclic models generally suppress the strong primordial ripples that many inflation models predict. That makes experiments decisive in principle. Observations from missions like Planck and searches for gravitational waves give constraints that favor some scenarios over others. Steinhardt and collaborators pushed the idea hard while inviting tests. Critics point to challenges in modeling a smooth bounce without runaway instabilities. They also stress that some versions require new physics beyond what is well established. Supporters reply that the model addresses deep puzzles about initial conditions and singularities in a natural way. The emotional payoff is striking. A cyclic cosmos feels less like a one-time miracle and more like an ongoing cosmic rhythm. That rhythm comforts some and unnerves others. If universes are born again and again, then the history of everything is an unending loop. The thought changes how we think about beginnings, endings, and the weight of our choices. Observers turned theory into tests. The clearest handle for the cyclic picture is the expected scarcity of strong primordial gravitational waves. If the universe bounced instead of inflating violently, then the sky should show weaker tensor ripples. That prediction made experiments decisive in principle. Teams trained telescopes and detectors to hunt for those ripples. Surveys of the oldest light tightened limits and forced model builders to refine their proposals. Some versions survived these constraints by adjusting the ekpyrotic dynamics. Others struggled with instabilities that threatened to spoil a clean bounce. Steinhardt engaged with the criticism openly. He worked with collaborators to show how matter and radiation could pass through a bounce without destroying the smoothness that the model needs. The debate pushed new simulations and sharper observational proposals. Beyond gravitational waves, there are subtler searches. People look for non-standard patterns in the large-scale distribution of galaxies and for traces of rare events that a bounce might leave. None of these searches has turned up a smoking gun. That reality is important. It shows how science progresses in fits and starts, and how bold ideas are kept honest by data. The emotional effect is complex. The cyclic model offers a comforting rhythm that removes an absolute beginning. It also asks us to accept a cosmos that repeats and perhaps erases. If time loops on large scales, what becomes of novelty and value? Roger Penrose. He proposed a cosmic story that folds time in a strange way. His model calls each eternal phase an aeon. The trick is conformal rescaling. Far in the future, black holes evaporate, and matter thins out until the universe has no scale. At that point, the infinite future of one aeon can be matched to the hot beginning of the next. The mathematics is elegant and unsettling. Penrose and collaborators argued that violent events in a previous aeon could leave faint marks in our oldest light. They searched the cosmic microwave background for concentric low-variance rings that might be echoes of collisions or black hole activity before our Big Bang. A team published claims that such rings appear in the maps. The claim electrified the field because it seemed to offer observable traces of a prior universe. Other groups pushed back. They showed how statistical methods and instrumental effects can create spurious patterns. Later, data and analyses weakened the original claim. Penrose answered by refining predictions and by stressing that absence of clear rings is not the same as absence of the mechanism. The debate is healthy. It forced better methods and sharper thinking about what a relic from a prior aeon would really look like. The idea matters for how we imagine beginnings. If our Big Bang is sewn to a universe before it, then creation is not a single one-off miracle. It is part of a chain. That chain changes the feel of existence from unique event to ongoing cosmic sequence. The thought is simple and disorienting. After the initial ring, claims the field tightened its standards. Teams rechecked statistics and examined how instrument noise and foregrounds can paint ghostly circles. The Planck satellite produced cleaner maps, and many original signals faded under that scrutiny. That sequence is not defeat. It is the scientific method in motion. Penrose responded by refining what a true imprint would look like and by pointing to subtler features that earlier analyses might miss. Researchers then developed more robust statistical tools and new templates for expected patterns. They also explored other relics, such as unusual distributions of cold spots or rare high-energy events that could betray a previous aeon. The search changed from a single dramatic claim to a disciplined program of model building and falsification. Some proposals remained tantalizing but fragile. Others collapsed under better data. The net effect is progress. Methods improved. Data sets grew. The conversation shifted from sensational headlines to careful limits and conditional predictions. The philosophical stakes stayed high. If conformal cyclic cosmology were correct, it would mean that our universe carries a faint memory of a life before the Big Bang. If that memory is encoded in tiny statistical quirks, then finding it would change how scientists think about origins and about causation across aeons. If the memory is not there, then the model still served a purpose by forcing new ways of reading the sky. The final thought is simple and urgent. These 10 scientists each glimpsed something profound about the nature of reality. Their work suggests that what we call the universe may be just one small part of something unimaginably vast. Whether through quantum branching, cosmic inflation, mathematical structures, or cyclic time, the evidence points toward a multiverse of staggering scope and complexity. The search for proof continues. New experiments probe the cosmic microwave background for echoes of other worlds. Quantum computers may someday demonstrate the reality of parallel computations. String theorists calculate the landscape of possible physics. But perhaps the most remarkable discovery is not any specific evidence for multiple realities. It is the realization that serious science, pursued with mathematical rigor and experimental honesty, leads us to consider possibilities that once seemed purely fantastic. These scientists did not set out to multiply worlds or challenge our sense of uniqueness. They simply followed the mathematics where it led. And it led to a cosmos far stranger and far grander than anyone had imagined. Whether or not the multiverse exists in any of these forms, the work of these 10 researchers has already changed how we think about existence itself. They have shown us that reality may be not singular but plural, not simple but layered, not finite but infinite, in ways that stretch the very meaning of those words. The final answer remains beyond our reach, but the question itself has transformed from science fiction to serious science. And that transformation may be the most important discovery of all